Welcome to the deep dive. So today we're tackling a really fundamental question in physics.
Yeah, a big one. Where do the laws actually come from?
Exactly. Where do the laws of physics, the rules that govern everything, actually originate? For centuries, the kind of default view was, well, the Newtonian clockwork universe idea.
Right, that there must be some uh, ultimate set of rules built into reality,
Yeah.
something external that makes matter behave in certain ways.
Yeah, like gravity is just there, forcing things to fall. It feels intuitive.
It does. I mean, why else would things work the same way everywhere, right? But the sources we're digging into today, they propose something, well, pretty radical.
Okay.
What if the laws aren't really rules for matter at all? What if they're just necessary restrictions on how physicists have to, draw their models?
Whoa, okay. Let's unpack that a bit. So you're saying the laws of nature might actually be rules for human descriptions, rules for the models.
Essentially, yes. That's the core idea. Our mission today, really, is to explore how demanding that our scientific models are objective, meaning they have to be independent of any particular viewpoint, how that demand might actually force us to generate the most fundamental physical principles we know.
So objectivity forces the laws, like conservation laws, the fundamental forces, all that.
That's the claim we're exploring. The models, they have to describe an objective reality, sure. But the form those models take, that depends on us.
On the observer, the physicist.
Right. And we have to insist on this principle called point of view invariance. Basically, your description of what happens can't fundamentally change just because you, say, started your clock at a different moment or tilted your lab equipment.
Okay, so I'm describing, I don't know, a ball flying through the air.
Yeah.
The basic physics, the equations have to work the same, whether I'm standing right there or watching from way over there, or whether I decide up is the y-axis or the z-axis.
Exactly. Physics can't care about those arbitrary choices we make. And here's the really powerful part. The claim is, when we insist on this point of view invariance, the big laws of physics, especially the conservation laws, they just sort of pop out.
Pop out. How?
They emerge not as cosmic rules, but as like mathematical consequences needed to keep that objectivity in the model.
Okay. Before we get to those consequences, though, we need the basics. How do we even define the things we measure in physics?
Ah, good point. The sources really emphasize that quantities we call observables are operationally defined,
Meaning?
meaning they're defined entirely by the procedure we use to measure them. It's not about some abstract essence. It's about the operation.
Okay, like time.
Time is a perfect example. We just define time as what a clock measures. That's it, the standard second. Now, it's defined super precisely using radiation from a cesium atom, but it's still fundamentally tied to a measurement procedure we all agreed on.
And this operational view, it really changed how we think about distance, too, didn't it? With the redefinition of the meter.
Hugely. Back in 1983, yeah. Distance isn't defined by some standard ruler anymore. Officially, it's defined in terms of time.
How so?
It's the distance light travels in a vacuum, in a tiny specific fraction of a second. So measuring distance fundamentally relies on measuring time with a clock.
That seems kind of circular almost.
Well, it highlights how intertwined space and time become in our models. There's this great thought experiment with Alf and Beth.
Okay.
Imagine Alf and Beth want to figure out how far apart they are, but they only have clocks and can send light pulses back and forth. No rulers.
What?
Alf sends a pulse. Beth reflects it instantly. Alf measures the total round-trip time on his clock. Then Alf just defines the distance between them as half that time delay multiplied by some constant, let's call it 2 hours.
Wait a second. If he defines distance that way, using a constant, hasn't he just built the constancy of the speed of light, 2 hours, right into his definition of distance?
Exactly. That's the crucial insight. He's essentially embedding Einstein's postulate from special relativity into the definition itself.
Isn't that cheating? Are we just making reality fit our math?
No, it's about making the model self-consistent and objective. The sources argue, look, what if Alf and Beth tried using something else, like throwing golf balls back and forth instead of light?
Okay, what happens then?
It breaks down. The time it takes the golf ball depends on how fast Beth is moving relative to Alf, right?
Huh.
So Alf would measure different distances to Beth depending on their relative motion. The model becomes messy, observer-dependent.
Ah, I see. So using light, with its constant speed by definition in this model, is the only way to get a simple, consistent spacetime where distance and time measurements work objectively for everyone.
Precisely. The constancy of $10 isn't something we necessarily prove about deep reality. It's a requirement for building the simplest, most objective framework for our models. Space and time become, the graph paper we draw our physics on.
We don't need to prove the paper is real in some ultimate sense, just that it lets us draw consistent pictures.
You got it. It's a tool, a human invention for modeling.
Okay, so if space and time are these frameworks built on operational definitions and the need for consistency, how does that lead back to the conservation laws? You said they pop out.
Right. This is where Emmy Noether's theorem comes in. It's a truly beautiful piece of mathematics from the early 20th century.
No Nether's theorem, I've heard of it. It connects symmetry and conservation.
Exactly. It provides a direct, rigorous mathematical link. If your physical model has a continuous symmetry, which is basically our point of view invariance applied to things like space and time, then there must be a corresponding conserved quantity.
So demanding a certain type of objectivity mathematically forces something to be conserved.
Yes. Let's take the big ones. If we insist that the fundamental physics, the laws in our model, must be the same no matter when we run the experiment, that's time translation invariance.
Okay, shifting in time doesn't change the rules.
Noether's theorem says that mathematical requirement forces the conservation of energy. It's the foundation of the first law of thermodynamics. If the universe somehow cared about the absolute time, energy wouldn't have to be conserved.
Wow. Okay. And the same for space. If the physics has to be the same regardless of where we are, space translation invariance.
That symmetry forces the conservation of linear momentum.
And if rotating our setup, changing our orientation doesn't change the physics, space rotation invariance.
That gives you conservation of angular momentum.
So energy, linear momentum, angular momentum, they aren't just three separate rules God decided on. They're all consequences of demanding our model doesn't care about absolute time, position, or orientation.
Exactly. One core principle, objectivity or symmetry, leads to all three. It's about the lack of preferred moments, places, or directions in our descriptions.
That reframes things significantly. And this applies even in classical physics, like Newtonian mechanics.
Oh, absolutely. Think about Galilean invariance, the idea that the laws of physics should look the same even if you're moving at a constant velocity.
Right. Physics on a smoothly moving train is the same as physics on the ground.
When you demand that invariance and look for the simplest possible force law that relates force, mass, and acceleration, you basically end up with Newton's second law, force mode. It's the simplest form that respects those space-time symmetries.
Huh. So even forcema is kind of forced by symmetry. What about things like fictitious forces, like when you're in a turning car and feel thrown outwards? Centrifugal force? That doesn't feel very objective.
Right, because it's fictitious. An observer watching from the outside doesn't see a centrifugal force pushing you out. They see inertia trying to keep you going straight while the car turns into you.
So why does the person in the car feel it?
The person in the car is in a non-inertial accelerating reference frame. To make Newton's laws still appear to work in their accelerating frame, they have to invent that fictitious force.
Ah, so it's like a mathematical patch they add specifically to preserve the form of the law, to maintain a kind of local point of view invariance for themselves, even though their frame isn't inertial.
You nailed it. It's a correction factor to keep the familiar law looking valid in their viewpoint.
That's clever. And didn't this idea of preserving conservation laws, this symmetry principle, come up dramatically with the neutrino?
Oh, big time. In the late 1920s, physicists were studying beta decay, where a nucleus spits out an electron. They measured the energy of the electrons, and it was a continuous spectrum. Some electrons had high energy, some low.
Why was that a problem?
Because it looked like energy wasn't conserved. If the nucleus decays from state A to state B, the energy difference should be fixed. The electrons should always come out with the same energy. And momentum and angular momentum looked like they weren't conserved either. It was a crisis.
People thought the conservation laws might be wrong.
Some did. But Wolfgang Pauli made this bold proposal. He said, maybe there's another particle being emitted, one we can't see electrically neutral, very light, that's carrying away the missing energy and momentum.
He invented the neutrino purely to save the conservation laws.
Purely. Based on the principle of invariance, the symmetry. The sources really highlight this. If the neutrino hadn't eventually been detected decades later, the implication wasn't just that Pauli was wrong about a particle. It was that the fundamental principle of point-of-view invariance, expressed through conservation laws, might actually be flawed.
So the commitment to symmetry, to objectivity, was so strong it justified predicting a whole new particle.
That's how central the idea is. And it gets even deeper when we move to modern physics and the fundamental forces.
Okay, so we've seen how space-time symmetries give us conservation laws. How do forces like electromagnetism fit in?
This involves generalizing the idea of symmetry. We move from global symmetries, where you make the same change everywhere at once, like shifting all clocks by 5 seconds, to local symmetries, specifically local gauge symmetry.
Local meaning. It changes from place to place.
Exactly. Imagine you have some property, like the phase of an electron's quantum wave function. What if we demand that the physics must remain unchanged, even if we change that phase differently at every single point in space and time?
That sounds like a much stricter requirement.
It is. And when you impose that requirement mathematically on the quantum description of a charged particle, like an electron, something amazing happens.
What?
The math forces you to introduce a new field, a compensating field, to keep the physics invariant under those local changes. And that field turns out to be exactly the electromagnetic field, mediated by a massless particle, the photon.
So the electromagnetic force itself is basically a mathematical requirement for maintaining this stricter local form of point of view invariance.
That's the essence of it. The force field acts like, well, like symmetry police, ensuring the description stays objective even under these point-to-point transformations. And the same basic idea, with more complex symmetries, gives rise to the strong and weak nuclear forces in the standard model.
The forces are consequences of demanding local objectivity. That's mind-bending. But wait, there's a catch, isn't there? Doesn't this local gauge invariance usually require the force-carrying particles to be massless, like the photon?
Yes, typically it does. The photon is massless. The gluons of the strong force are massless.
But the W and Z bosons, the carriers of the weak force, they're incredibly massive, heavier than iron atoms. How does that work?
That's where spontaneous symmetry breaking comes in, usually involving the Higgs mechanism.
Spontaneous symmetry breaking sounds intriguing.
Think of it like this. Imagine a perfectly sharpened pencil balanced perfectly on its tip. That state is perfectly symmetrical. It looks the same from all horizontal directions.
Okay, but unstable.
Right. The slightest nudge or even just quantum fluctuations, it will fall over, pointing in one specific arbitrary direction. The underlying laws of physics governing the pencil are still perfectly symmetrical, but the actual state the pencil settles into lying on its side has broken that symmetry.
So the fundamental rules still have the symmetry, but the outcome, the reality we see, doesn't necessarily show it.
Exactly. In the early universe, things might have been in a highly symmetric state where particles related to the weak force were massless. But as the universe cooled, it settled into a lower energy state, like the pencil falling over mediated by the Higgs field. In this lower energy state, the symmetry is hidden or broken, and particles like the W and Z bosons acquire mass.
So the complexity we see, like mass, can arise from a simple underlying symmetry being spontaneously broken.
Precisely. The apparent complexity emerges from the history and the state the universe settled into, not necessarily from complex fundamental laws.
This whole picture seems to move away from that old clockwork universe idea. Newton's view is deterministic, right? If you know the position and momentum of everything now, you know the entire future.
It was a perfect clockwork machine. But quantum mechanics, which is built on these very symmetry principles we've been discussing, throws a wrench in that with Heisenberg uncertainty principle.
Right. You can't simultaneously know a particle's exact position and exact momentum.
Which fundamentally means we don't live in a purely deterministic clockwork. The future isn't perfectly predetermined from the present, even in principle. There's an inherent element of, well, randomness or chance baked in.
So physics doesn't just deal with necessity, things must happen, but with probability.
Yes, quantum mechanics gives us powerful tools to calculate the probabilities of different outcomes. Most probabilities aren't just 0 or 1, impossible or certain. They lie somewhere in between. Chance plays a fundamental role.
So wrapping this part up, the picture emerging is that the laws are maybe ruleless rules or lawless laws. They aren't dictates from on high, but consequences of demanding objective description in a universe that allows for chance.
That's a great way to put it. They seem to be the inevitable structure that arises from demanding consistency and observer independence, almost the laws of the void, which you get when you don't have a specific plan dictating everything.
It's a compelling picture,
Yeah.
but it can't be perfect, right? Our models are human creations. Is there anywhere this beautiful symmetry-based structure dramatically fails?
Oh, yes. There's one absolutely colossal failure staring us in the face, reminding us that our models are just that, models. It's the cosmological constant problem.
Also known as the vacuum energy problem.
Exactly. Quantum field theory, built on all these principles, predicts that even empty space should be fizzing with virtual particles popping in and out of existence. This gives the vacuum itself an energy density, a kind of zero-point energy.
Okay, seems plausible. What's the problem?
The problem is the value the theory predicts. When physicists calculate this vacuum energy density based on the Standard Model and quantum field theory, the number they get is enormous. It's staggeringly huge.
How huge are we talking
We're
about?
talking about something like 10, 20 times. That's a 1 followed by 120 zeros times larger than the energy density we actually observe in the vacuum of space.
120 orders of magnitude. That's not just wrong, that's spectacularly, hilariously wrong.
It's arguably the worst theoretical prediction in the history of physics. The observed energy density of the vacuum, which we associate with dark energy driving the universe's expansion, is incredibly tiny by comparison.
So what would happen if the theoretical value is right, if the vacuum really had that much energy?
The gravitational effect, because the energy curve space-time, according to general relativity, would be overwhelming. Space would be expanding or contracting at such a fantastic rate. Well, structures like galaxies, stars, planets, even atoms probably couldn't form. You wouldn't be able to see your hand in front of your face because space would be curving so wildly.
So the universe as we know it simply couldn't exist if our current model's prediction for vacuum energy were correct.
Precisely. It's a profound failure that tells us there's something fundamental we're missing, some deep flaw in how we combine quantum mechanics and gravity, or perhaps in the very concept of zero-point energy itself. Our models, despite their incredible success based on symmetry, are definitely incomplete or incorrect at this very fundamental level.
Okay, so let's try to sum up this whole deep dive. The core idea is that the universe seems comprehensible, the laws seem consistent, largely because we structure our descriptions, our models, to be objective.
Right. We insist on this point of view invariance, this symmetry. And that insistence, mathematically, seems to generate the great conservation laws and even the structure of the fundamental forces.
So the success of physics might be less about discovering pre-existing external laws written into the fabric of reality, and more about the power of constructing consistent, objective, and often mathematically simple models based on observation.
That's the perspective, yeah. Makes the laws feel less like constraints on the universe and more like constraints on us, the describers.
It leads to that provocative idea you mentioned,
Yeah.
the lawless laws. The universe looks remarkably like it would if there weren't any overarching metaphysical governing plan, but just the requirement that any valid description has to be objective.
It's a powerful thought. Whether ultimate reality is simple, like atoms in the void, or something more abstract, like mathematical forms, our models work because they adhere to these principles of invariance.
Which leaves us with a final thought for you, the listener, to mull over. If our physics, our most successful way of understanding the cosmos, is fundamentally shaped, perhaps even forced, by our need for objectivity and simplicity.
What does that tell you about the deep nature of reality itself versus the nature of human knowledge? Are we truly uncovering the universe's blueprint, or are we seeing the reflection of the tools and rules we must use to make sense of it all?
Something to think about.